Hey everyone and welcome. Today we're going to crack the code on one of the most important ideas in all of chemistry. It's a process that is happening everywhere, all the time, all around you, and even inside you right this second. We're talking about oxidation and reduction, or as chemists call for short, redox. And you might be surprised what connects a delicious barbecue to a rusty old bike.
I mean, think about it. That amazing crust on barbecued meat, the sad-looking red-brown rust on a bike that's been left in the rain, or shoot, even just breathing in and out to get energy. They all seem like totally different things, right? Well, it turns out, chemically, they're all part of the same family. They are all redox reactions, this constant back and forth that literally powers our world.
So where do we even start with this? Well, the easiest way in is to look at the very first definition, the one that's based on the element that gives oxidation its name, oxygen. This is the kind of chemistry you can actually see with your own two eyes.
And this shows you the two sides of the coin perfectly. Over on the left, you've got rusting. An iron bike frame meets the air. It gains oxygen, and it forms that crumbly reddish-brown rust we all know. But on the right, in a massive blast furnace, the complete opposite happens. Iron ore, which is basically just pre-rusted iron, gets superheated to strip that oxygen away, leaving behind pure, strong iron. See? One is a gain of oxygen, the other is a loss.
Okay, let's put a name on it. When something gains oxygen, we say it has been oxidized. So with rust, the iron atoms grab onto oxygen atoms from the air, and they form a totally new substance, iron oxide. That's what you're seeing in the chemical equation right there.
And yeah, you guessed it, the opposite of that. The loss of oxygen is called reduction. In that blast furnace, the iron ore, the Fe2O3, loses its oxygen and it's reduced back to pure iron, or Fe. Now, the key thing to remember here is that these two are partners. They're a package deal. You literally cannot have one without the other. If something is losing oxygen, something else has to be gaining it.
Okay, this oxygen definition is a great start, but it's got a pretty big limitation. It really only works when oxygen is part of the reaction. To get what's really going on, we have to zoom in, like way in, down to the subatomic level. Because it turns out it's not actually about oxygen, it's all about electrons.
So, if it's not always oxygen, what is the one thing that's always being passed back and forth in every single one of these reactions? The answer is so important, so central to chemistry, that there's a really great little trick to remember it.
All right, here's the first half. Just burn this into your brain. Oxidation is loss.
And the second part, reduction is gain. Okay, put them together. What do you get? Oil rig. Oxidation is loss. Reduction is gain. Of what? Of electrons. That's it. That's the real secret. Every redox reaction is just a transfer of these tiny, negatively charged particles we call electrons.
Let's go back to our rusting iron. See, with this equation, the neutral iron atom, Fe, turns into a positively charged Fe3+ ion. How? Well, it has to give up or lose 3 negative electrons. That loss of electrons is oxidation, OIL. Oxidation is loss.
So, where do those electrons go? They don't just vanish. The oxygen atoms from the air are right there to snatch them up, and you can see it here. Each oxygen atom gains electrons and becomes a negative ion. That gain of electrons is reduction, rig. Reduction is gain. It's a perfect trade. One thing loses, the other one gains.
Okay, so oil rig is fantastic, but how do you keep track of all this electron movement in really complicated reactions, especially if there aren't obvious ions floating around? For that, we need the chemist's master key, a little idea called oxidation states. This is the tool that lets you figure out any redox reaction.
The easiest way to think about an oxidation state is like a pretend charge. It's a bookkeeping system, a way for us to track where the electrons are. We just assign a number to every atom in a compound that tells us if it's gained or lost some control over its electrons compared to when it was all by itself.
And here is the simple rule that makes the whole thing work. If an atom gets oxidized, meaning it loses negative electrons, its oxidation state goes up.
it becomes more positive. And if an atom gets reduced, meaning it gains negative electrons, its oxidation state goes down, becoming more negative. An increase is oxidation, a decrease is reduction. It's that simple.
So how do we find these numbers? Honestly, it's just a simple logical puzzle. First, you start with a few elements where we pretty much always know their oxidation state. Second, you remember that for a whole compound, all those numbers have to add up to 0. And third, you just use a little bit of basic algebra to figure out the one you don't know.
Now, here are the official rules. Don't let the table scare you. The details are all here, and you can just pause the explainer if you want to get familiar with them. The big ones to remember are that any element all by itself is 0, and oxygen is almost always -2. Let's give it a try.
All right, let's actually use these rules. The example here is sodium carbonate, Na2CO3. Okay, so from our rules, we know each sodium, Na, is +1, and each oxygen, O, is -2. So let's do the math. We have 2 sodiums, so that's a total of +2. We have 3 oxygens, so that's a total of -6. The whole thing has to add up to 0. So what does that one carbon atom have to be for it all to balance? Well, +2 and -6 is -4, so the carbon has to be +4. See? It's just a puzzle.
Okay, just one last bit of language to get down. In this whole redox dance, the thing that causes oxidation is called the oxidizing agent. It does that by taking electrons, which means it gets reduced itself. And the thing that causes reduction is the reducing agent. It gives its electrons away, which means it gets oxidized. They're always working in a pair, one causing the other.
So why on earth did we just learn all that? Because once you get redox, you start seeing it absolutely everywhere. This isn't just some abstract thing from a textbook. This is the chemistry of life, of technology, of everything. This is the payoff.
Just take a look at this. Respiration, the process you use to burn food for energy, is oxidation. And photosynthesis, what plants do with sunlight to make that food in the first place, is reduction. They are the exact reverse of each other. This perfect redox cycle, this electron transfer powered by the sun, is the engine that runs almost all life on this planet. It's incredible.
What about the phone in your pocket or the laptop you're watching this on? They all run on batteries. And what is a battery? It's nothing more than a carefully designed redox reaction, set up to make electrons flow through a wire instead of just jumping across. When you charge your phone, you're just using electricity to force that redox reaction to run backwards, getting it all set up to go again.
And check out this amazing medical tech. You know that little clip they put on your finger at the doctor's office, the pulse oximeter? How does it instantly know the oxygen level in your blood? It shines a little light through your finger, and it turns out the hemoglobin in your blood actually changes color slightly depending on if it's carrying oxygen or not, and that change is because of a redox reaction. It's a life-saving tool built on the very same ideas we just talked about.
So when you boil it all down, what is redox? It's why things rust and burn. It's the secret inside every battery. It's the engine of life itself through photosynthesis. It's an incredibly powerful tool for figuring out what's in things. But at its heart, it's really just a story about electrons on the move.
So now you're in on the secret. You get the invisible dance of electrons that makes so much of our world work. So my question for you is, what everyday reaction, from striking a match to just watching an apple slice turn brown, are you never going to see the same way again? Thanks for watching.